Welcome to the introduction of Trackmatcher, a package for track interpolation and intercept finding. In atmospheric sciences, we often have the need for collocation of data from different sources for synergistic analysis. To do this in an automated and objective way, we've developed Trackmatcher. Trackmatcher finds intercept points in pairs of trajectories. And as a trajectory, we define the three-dimensional path depending on latitude, longitude, and altitude over time. The package is widely applicable in geosciences, and it's easy to adjust to user needs. We implemented parameters that compromise between the model performance and the precision of output. And it's easy to add new functions, for example, to extend to different data types. Currently, Trackmatcher is able to process aircraft and cloud track data and compares them to satellite ground tracks. Data that might be added in the futures include ship tracks and air parcel trajectories. Trackmatcher is an open source project available at GitHub. We have the lim-aerocloud organization that hosts the main package, trackmatcher.gl, and the package for track interpolation, PCHIP.gl. But there are further tools, so please feel free to explore the lim-aerocloud organization. Today, I only want to talk about technical aspects and leave any scientific results out. I'd like to trigger a discussion about the algorithm and performance computing and big data processing in general. I'm not a software engineer by background, so I'm always grateful for some tips here. And of course, I'd like to demonstrate a use case of Julia in environmental sciences. In short, our track matching algorithm works in 4 steps. First, we load the track data, then interpolate those tracks and find intersections in them. Finally, we save the model output and any observations near intercept points. Input data are loaded from CSV, TSV, MATLAB or HDF4 files. And to read the old HDF4 file format, we currently use MATLAB, and therefore Trackmatcher relies on a MATLAB license. We distinguish between 2 types of input data. Primary data are organized as individual trajectory and stored in a unified format. Those individual tracks get then combined in a vector and are stored in a data set, which can hold different vectors for different sources of the same data type. Secondary data are a single long trajectory stored in a continuous format. We implemented a type tree in Trackmatcher that organizes all of our experimental and computed data. And to initiate a process in Trackmatcher, such as loading data or calculating intersections, you just need to instantiate the appropriate struct. And constructors that can do this have a red boundary in the plot given here. And you can do this all in once using the dataset constructor. We chose the PCHIP method for our track interpolation, the piecewise cubic Hermite interpolating polynomial. And this method has the advantage over all of the other interpolating methods that it can predict curves with sharp bends in it really well. So the advantage here is that the method does not demand a continuous second derivative and therefore shows no artificial oscillations at discontinuous sides of a track. So whenever you have a bend in your curve, as it can always occur in a flight track, for example, PCHIP predicts it very accurately and really was our go-to method here. So if you're interested in the method, please feel free to pause the video and explore the equations of the polynomial or any references given here. Now we come to the core part of Trackmatcher, finding intercept points in pairs of trajectories. But first we need to constrain the data of the secondary data set to the primary data. Therefore, we first load the primary data and then only those data points of the secondary data set that are within the time frame of the primary data. We put a bounding box around the primary trajectory and consider only the track segments of the secondary dataset that are within this bounding box. In those track segments, we need to find our intercept points. To do this, we calculate lat long pairs for the primary and the secondary dataset and subtract those coordinates from each other to find the minimum distance between them. Where the distance reaches 0, we have our intercept point. To be able to subtract coordinate pairs, they need to be in sync and have a common x value, either latitude or longitude, and a common step range. And as our original data is highly irregular, we need the interpolated data from the previous step. We use those interpolated track segments to define our distance functions, where we subtract the coordinate pairs. In this distance function, we need to find the roots, and those roots are our intercept points. To find those roots, we use the IntervalRootFinding package as a core part of our track matching algorithm. And with a working algorithm, we can test its performance. We used two different datasets to test the performance. One was from the Bräuer data center and included 558,000 global flight routes, and we found almost 20,000 intercept points in them. However, data processing was really slow and took 16.5 hours. So we took a much smaller dataset from the FlightAware archive, where we had 37,500 selected flight tracks over the Pacific, and we found about 1,000 intercept points. To our surprise, the processing was even slower and took more than twice as long. So we are really puzzled here why the algorithm is so slow and why is it dependent on the data source. It shouldn't be, as the data is stored in a unified format. What is promising though is that we get very accurate results. For the second dataset, we have a mean accuracy of 7.5 meters, and that mean lies at the 94th percentile. So almost all of our data is predicted within a few meters. There were only 16 data points with an accuracy above the standard deviation of 64 meters, and that corresponds to about 1.5% of all the intersections found. I should also mention that there can be large gaps in the track data, especially over the open ocean, and that is represented by the distance of the calculated intersection to the nearest measured track point, which is on average 110 kilometers, but can get up to 2,500 kilometers. So we implemented a threshold to exclude those highly uncertain calculations that are far away from a measured track point. And you should make use of this threshold if your dataset allows for it. So in the near future, we like to do more performance evaluation and possible improvements, for example, by parallelizing the code. We also want to move away from the MATLAB license by using open source software to read HTF4 files. And that could be, for example, Python or Fortran wrappers. If you are interested in Trackmatcher, please look out for a paper currently in preparation either for GMD or AMT. And with that, I'd like to thank you for your attention, and I'd like to especially thank Matthias Tesche, who came up with the idea of the Trackmatcher package and guided the project throughout the way. And I'd like to thank our funding agency, the German Federal Ministry of Education and Research, through the MOPGA-CRE initiative. Thank you.